The distinction between absolute theories of time and relational theories of time is analogous to that between absolute theories of space and relational theories of space. According to the relationalist concerning time, time cannot exist unless there are motions or changes. According to some philosophical perspectives, you really can't have change unless you have motion. So that would make a relational theory of time would hold that in order to have time, we must have motion. It's not clear that that's necessarily true. You can imagine ontologies on which you could have time without motion. For example, if you believe in the possibility of non-physical or Cartesian souls, you could imagine these non-physical souls undergoing changes even though they weren't in any kind of space. Clearly they could undergo psychological changes. They could be happy and then sad and then happy again and so on. So these would be changes, and a relational theory of time could hold that provided that any changes exist, whether those changes are changes in unlocated souls or changes in the velocity or direction of motion of a material object, time can exist based on these changes, whether they be motions or changes of these other sorts. The main idea behind the relational theory, then, is that you can't have time without change. So, without changing objects or events, there would be no time, according to the relational theory. The absolute theory of time, on the other hand, maintains that time exists independently of the existence of any changes. So a universe that was completely devoid or empty of all objects, which contained no motions or changes of any sort whatsoever, could still consist of time. According to the absolutist, time flows along or passes regardless of whether it can be measured by using various motions or changes. The consequence of this seems to be that if all motions or changes were to cease, then time would also cease. So you could imagine a world where time is moving along, and then everything just freezes in place. Then time would stop existing. And if change or motion resumed, then time would start again. So you could have a world which is gappy in this way, where you have changes in time, and then no change, and then change again in time. would commence once again. So if you imagine, say, a universe where, say, there's a stopwatch. This is out of an old episode of Twilight Zone, an old show from the 1960s, science fiction type of show, where this fellow had a marvelous stopwatch, and if you press the button on it and the watch stopped, then everything in the universe, aside from the person who had the watch, that is, would freeze in place. So this wouldn't exactly meet the conditions, because the person with the watch would still be changing. But if you just extend that to include everything ceasing, then you'd have the picture. There's no reason in principle, as far as I can see, why you couldn't have a world where there was motion and then cessation of motion and then resumption of motion. So it seems to be possible on the relational theory for one to have gappy time in this sense. So for the absolute theory of time, though, it wouldn't make any difference whether changes were occurring or not. Time would necessarily exist, it seems, regardless of whether there was change or motion. So time would just independently exist independently of any change whatsoever. All right, let's now focus on absolute space. One of the most important and discussed arguments in favor of the doctrine that space is absolute was put forth by Sir Isaac Newton, the discoverer of many of the principles of physics, basically regarded as the codifier of classical physics. He defended absolute theories of both time and space, though we're going to focus on his views about space today. He gave several arguments in defense of absolute space. The first and perhaps most well-known is his argument concerning the rotating bucket. Newton asked us to imagine a universe in which nothing exists except for three things: a bucket, liquid water in the bucket, and a rope affixed to the bucket handle going upward. And there's nothing else in the universe except for the rope, the bucket, and the water in Newton's original example. And he asks us to imagine that the bucket has been rotated around so that the cord or rope attached to the handle is all very tightly twisted. Okay, so what would happen to the bucket given the cords being twisted? Well, obviously we know that the bucket would begin to rotate or spin as the cord unraveled. At first, the water in the bucket would not exhibit any motion. It would be at rest in relation to the bucket and the rope. However, at a certain point, the motion of the rotating bucket would be transmitted to the water, and it would begin to rotate in the same speed and direction as the bucket. Now, at that point, the water would be actually at rest with respect to the walls of the bucket, relationally speaking, because it would be moving around with the bucket at the very same speed as the bucket, and would also be moving at the same velocity as the rope is unraveling. At that time, however, the water will have certain properties by which it can be known to be the case that the water is actually moving, even though it's not moving relative to the walls of the bucket or the rope. This is because of centrifugal force. The centrifugal forces in question will cause the water, as it rotates, to become concave and lap up the sides of the bucket. So by observing this fact, it's evident that the water is rotating, even though it's not moving in relation to the bucket. So when the bucket first started to spin, the walls of the bucket are moving in relation to the water, but later on, the water and the walls of the bucket are at rest with respect to each other, but it can be deduced that the water must be rotating because of the centrifugal force effects which cause it to lap up the sides of the bucket. This is something intrinsic to the water inside the bucket by which it can be deduced that the water is rotating. This appears, on the face of it, to be a kind of absolute motion, which Newton interprets in terms of things moving not in relation to other objects, but moving in relation to absolute space itself. So Newton's argument basically goes as follows. There is a time at which the water shows the effect of centrifugal force, but at that time the water is not moving relative to the bucket or any other material thing. Well, you might think that it's moving relative to the ceiling or something like that, to which the rope is attached. But in this thought experiment, we're supposing that there isn't any ceiling. Remember, there's only three things in the universe: the rope, the water, and the bucket that contains the water. Actually, Newton could have dispensed with the rope as well. He could have supposed, as an abstract possibility, and why not, that the only things that exist in the universe are the bucket and the water, and that the bucket is rotating. You may say, well, how did the bucket get to be rotating? What caused it to rotate? Well, the answer might simply be that it's part of the initial conditions in that universe, that is the starting conditions of the universe, that there's a rotating bucket of water. Newton's got to make a similar assumption if he's going to suppose anyhow that there's a bucket of water with a rope attached, because it would have to be part of the initial conditions. It seems that the rope is twisted and wound up so that it will subsequently unwind. There doesn't seem to be any special problem about assuming initial conditions. It seems that we have to make some assumption like that about any universe that we suppose existing. Or elsewise, we just go back and back and back, supposing a universe that's infinite in time. Perhaps we can imagine universes that are infinite in time, but we can also imagine ones that start at a certain point, it seems. So Newton's assumptions in his thought experiment of the rotating bucket seem quite defensible. So at any rate, so there's a time at which the water is going to display these centrifugal force effects, even though the water's not moving relative to anything else in that universe, either the bucket or the rope. Okay. Newton's second premise is that all centrifugal force effects are produced by rotational motion. Therefore, there's a time at which the water is moving, lapping up the sides of the bucket, but it's not moving relative to any other material thing that exists, either the bucket or the rope, all of which are moving along with the water. Moreover, motion that's not relative to any material thing must be absolute motion, that is, motion with respect to space itself. So, in conclusion, the water is moving with respect to space itself, and so there must exist such a thing as absolute non-relative space. So what Newton is saying here is that accelerated motion, which can be either a thing's increasing its velocity over time, or a thing's constantly changing its direction over time, which is what you have in the case of of rotational motion, such as the motion of the bucket, constantly changing its direction, which is measured by a straight line, touching attached to the rotating object. So that line will constantly be changing its direction as the bucket rotates around, and that counts as accelerated motion for the purposes of physical laws. So rotational motion is a special type of accelerated motion. So this accelerated motion, the water's constant change of direction, evinces itself in this effect of the water lapping up the sides of the bucket, and proves the existence of absolute space and accompanying absolute motions. One of the objections raised to Newton's argument was put forward by the idealist George Berkeley, and a similar objection was later put forth by Ernst Mach, who was a sort of logical positivist. Both Berkeley and Mach are skeptical of Newton's assumption that centrifugal force effects would be exhibited by the water in the rotating bucket if there was nothing else in the universe aside from the bucket and the water, or the bucket and the water and the rope. Berkeley's skeptical of whether the water would actually lap up the sides of the bucket if there was nothing else in the universe. He thinks that there would have to be other things like the fixed stars out there in order for centrifugal force to be manifest. Ernst Mach makes a similar objection. So according to Mach, without the fixed stars out there, we wouldn't see the water lapping up the sides of the bucket. There would be no centrifugal force effects. Now it seems that the laws of physics as we know them, would hold even in a universe without fixed stars. So, I mean, it's not clear on what grounds Mach would establish his contention. So, his objection seems somewhat problematic in that respect. There's no real way to settle the matter, of course, by direct observation. The way things stand, we really can't given that the universe has the properties that it has and contains the vast number of stars that it does, we have no way of telling what would be observed if there was nothing in the universe but the water and the bucket and the rope. There's no way to tell by observation, in other words, what would happen if all the stars were to vanish, and if there were nothing but the water, the bucket, and the rope. No way to tell what would happen one way or the other. Now, one of the interesting things here has to do with a second version of Newton's argument. Newton provided a second, somewhat different example to argue for absolute space. On this example, according to this example, you've got, say, two cannonballs connected by a rope, and we're to imagine that the two cannonballs are moving in a circular motion. That is, the two balls are rotating in a kind of pinwheel motion, the center of which is the midpoint on that rope connecting the two cannonballs. So they're moving around like this, going round and round. In that case, what would occur, given the laws of physics, is that the rope connecting the two cannonballs would become extremely taut. So if they weren't moving, the rope would just be connecting them, but as they rotated, the objects would tend to be flying outward, and so the rope would tighten and become extremely taut. So this would give us a way of knowing that, or concluding that the cannonballs are rotating around the midpoint of the rope, even if there was nothing else in the universe but the two cannonballs and the rope. So we're to imagine that nothing else exists in the universe except for those three things. It would still follow that the cannonballs are rotating around the midpoint of the rope as a result of the fact that the rope is extremely taut. Interestingly, the equations of Einstein's general theory of relativity yield the consequence that the rope would become extremely taut, even if those were the only three things in the universe: cannonball 1, cannonball 2, and the rope. So in this example, it seems like it appears that Mach's argument would have to be that if there was nothing else in the universe than these three things, if there was nothing else in the universe but these three things, the rope would not grow taut. But as I'm noting, this is not confirmed by current physical theory, including Einstein's theory of relativity, which is often cited by those who want to say that space and time are relative and not absolute. Einstein's general theory of relativity, at least, doesn't have that consequence. Interestingly, it's got the consequence that even if you just had these three things in the universe, there would be a tightening of the rope, suggesting at least that there is such a thing as absolute motion. Newton's conclusion, once again, is that space must be absolute to explain these results. Putting aside Mach's reservations, then, does Newton's argument establish that there's absolute space? Well, probably not. There's still one other premise, which historically was not called into question, but which on closer examination and reflection creates some uncertainty about the argument. The uncertainty in question has to do with whether these arguments are enough to establish the existence of absolute space, or merely show that either there's an absolute space, or that motion is an absolute or intrinsic property of a moving object. So the claim here is that these thought experiments involving the rotating bucket of water and the cannonballs connected by a rope that are spinning in a circle around the center point of the rope. Are insufficient to establish the existence of absolute space, and may only show that motion, bodily motion, is an intrinsic property of the moving object, and hence may only show that motion is absolute as opposed to space being absolute. The crucial assumption made by Newton in these arguments is that motion is some kind of relational property. Relational theorists of space think that motion is a relational property involving a change in the relations of one body to another body. Absolute theorists of space, similarly, to a certain extent, suppose that motion of a body is a relation between that body and absolute space. So there's a common assumption here that motion is a relational, a change in a relational property, changing one's position relative to something, either to absolute space itself, or in relation to some other body, as the relational theorist of space would hold. On the other hand, if motion is an absolute or intrinsic quality, that is, a quality of an object that it has in and of itself, and not a property that it has in relation to something else, then we're not going to be able to conclude, even if the motion of the water in the bucket is absolute, that is not in relation to any other objects, material objects in the universe. We're not going to be able to conclude that the motion of the object presupposes the existence of an absolute space, because the motion of the object won't be defined in terms of its relation to places or bodies, but it'll be an intrinsic quality of the object itself. It'll be a property like, say, size or mass or shape. These are properties that are typically or generally thought to be intrinsic properties of a thing, properties that the thing has in and of itself and not in relation to something else. Say, as opposed to an object's distance from another thing, which is obviously a relational property, a property a thing has in virtue of its relation to another thing. So if these doubts are right, then perhaps Newton's argument doesn't establish that there's an absolute space exists, but only the weaker conclusion that either there's an absolute space if we think of motion as a relational property, or objects can have absolute motions, motions that they have in and of themselves and not in relation to any other entity, whether it's space itself or some other material object. At any rate, the dispute between those who hold relational theories of space and absolute theories of space is to this day an unsettled controversy. And similar remarks apply to the dispute between those who hold relational theories of time and absolute theories of time. That controversy as well still continues among philosophers and physicists alike.